Okay, it's 8 o'clock and I should start our discussion on our cooking lecture. And for this lecture, I should start with the elastic beam theory again before we move to the conjugate beam method. The elastic beam theory is the backbone of the study of the deformation of the elastic beam. And basis upon this theory, as you may know, you may take a ruler and then it's you bend after you put the point load at the end pocket, and then you should observe one thing. When the load is small, the bending of the beam, this is fixed. So we sub A y equal to 0, V sub AX equal to 0, theta sub A gonna be 0. When P is small, the deflection of this one gonna be small like this one. When you increase the force P, the deflection gonna get larger, and when the P is gets larger, the deflection gonna get larger like this. What happened? The bending of this one is not directly due to the applied force, but the deformation of this one is due to the bending moment, large P produce large M, and then produce large deflection. And then basis upon this one, the theorem starts with the consideration of the deformation. If we let's consider the distance x measure from point A, that means every time we talking about the elastic curve, this is gonna be, oops, sorry, no one tell me about it. I also didn't see it. Very bad on that. Anyway, large deformation due to large P. Okay, the first one, the second one, and the third one. Okay, basis on this one, since this is the point A with the fixed support, again, the deflection that occurs at point A will increase when the load P is small. The deflection over here is small. When load P is large, again, the deflection over here getting large when the load P increase, and then the deflection over here increase like this one. But due to the deflection related to the slope, if you use this horizontal line as the reference, usually this is the line passing through the centroid of the beam. Then if you draw the tangential line over here, you will get this one as the form of slope. Okay, so slope is just the first derivative of the deflection with respect to x. And then if you do the second derivative, you will get the curvature, and the elastic beam theory relate the moment to the deflection with the form of this equation of what? Of the moment equal to EI, and then times the curvature. And then if you see this one, what's going to be the EI? E is going to be the modulus of elasticity. If you consider the steel, this is going to be 200 gigapascal. If you consider the wood, this can be only 5 gigapascal. So if you use material with large thickness, the deformation is going to be less. Okay, and then following this one, what's going to be the I? I is going to be the moment of inertia. If this is B, this is D, the moment of inertia about the neutral axis will be BD cubed over 12. If this is the steel, okay, again, you go to the steel table and then you can select the moment of inertia from that. Based upon this one, we have the double integration related to the differential equation that you study in the differential equation for civil engineer. However, there are Professor Ottomore, okay, coming up with a very good idea to compute for the deflection, to compute for the slope. Based upon his concept, he start with the consideration of the leadership of what? Of the shear force of this bending moment and distributed load. We start with this equation. If you recall, this is what? This is the slope of shear diagram. Okay, slope of shear diagram at any point, equal to what? Equal to any point equal to what? Equal to negative of the distributed load. And then we have the second one, the slope of the moment diagram at any point equal to the shear force at that point. We use this one in the drawing of what? Of the shear diagram and moment diagram by using the graphical method. Now, we rewrite this equation again. And then following this one, if we change, just take the V equal to this term, and then we rewrite the equation again. We get the second derivative of the bending moment equation with respect to x equal to minus w. Then Professor Ottomore come to the relationship between what? Between the deflection, between the slope, and then between the elastic weight. He come again with this equation. This equation, Ajahn just said, this is elastic beam theory. Mathematically, you may rewrite this term to be this one, right? And then you may say, okay, if you write this one, this term can be the term of the theta. Now, compare between two sets of this equation. We will have the form of what? The real distributed load. I should say this is the real distributed load. Equivalent to what? Equivalent, I should say, equivalent to what? To M over EI. And then we said that's gonna call elastic weight. Okay, if you know the function of M divided by EI, that's gonna be elastic weight. And then if you use this elastic weight, okay, if you use this elastic weight, compute for the shear force, okay, and I should say the elastic weights have the opposite side with the W downward positive. That means M over EI upward is positive. This one downward positive. Since it is have negative side, so this is upward is negative is positive. Then, if you use this elastic weight to compute for the shear force, okay, you will get what? You will get the function of the slope. Okay, you do the calculation on the conjugate beam using the elastic weight to compute the shear. The shear gonna be the slope, and then we will see the shear in conjugate beam due to the elastic weight is the slope at that point in the real beam. And then if you consider the equation here, you compute for the moment on the conjugate beam, you will get the deflection on the real beam. Okay, following this one, let me show you the calculation procedure. We have the real beam. Okay, this one will be given in your examination, and this one will be analyzed for what? For the deflection and for the slope. The beam subjected to the load W. Okay, and then you guys have the knowledge of what? Of the engineering static. You can do what? Compute for the reaction. Okay, so basis on this one, you may compute for the reaction AY and BY. However, you don't know the deflection that's occur over here. This is gonna be the deflection. This is gonna be the slope. Okay, the slope on the left and the slope on the right, they are equal. Okay, and measure what? Measure from horizontal up to the tangential line over there. Then you do what? After you get the deflection, after you get the reaction, you do the second thing. You draw the shear diagram. Then you use the same knowledge as you do, just draw this diagram. Okay, but this is A sub y, this is upward, and then dv by dx equal to minus w. Okay, and then you arrive at this point of what? By v sub b minus v sub a equal to negative of area of w between a to b. You will get this one, and for sure this one gonna be positive WL over 2. This one gonna be negative WL over 2, and then v sub y just positive. Now you do the third thing. You gonna draw the moment diagram. Okay, by using this one, the moment diagram gonna be something like this. We start with this to be 0, and then this is going to be the slope dm by dx equal to v. Okay, and then at this point we have 0 shear. So over here we have dm by dx equal to 0, and this is gonna provide the moment m max. Okay, over here we have m max also, and then the slope over here gonna be minus WL over 2. This again dm by dx equal to the shear over here. Now this is the previous knowledge that you can analyze the real beam. Okay, and go back to the previous slide. We got to what? We got to determine the elastic weight, and then when we get the elastic weight, we will draw the conjugate beam. Okay, another beam that's going to help you to determine the deflection and the slope. Now, taking picture C, this is going to be the moment diagram and divide it by fractional rigidity. Okay, you will get the elastic weight. Okay, however, elastic weight gonna act on what? On the conjugate beam. Okay, and then I should say something. At point A, we have the boundary condition. Boundary condition of what? Boundary condition of theta sub A won't be 0, and v sub A equal to 0. Okay, and before that we have the concept of what? Concept of the slope that occur in the real beam. Okay, that's gonna be equivalent to v prime on the conjugate beam. And then for this one, you also have the deflection on the real beam. Okay, it's gonna be equivalent to the m prime on the conjugate beam. Now we got to determine these two things. The what? The shear on conjugate beam and the what? The moment on the conjugate beam. Based on this one, you can compute for the reaction over here, And due to the symmetry, everyone can compute half of the elastic weight will distribute to this point A part. Another half pocket will distribute to this point B part. Okay. Now, what happened? This is going to be the A sub y part. This is going to be B sub y part. And then if you just consider over here, the point A subjected to A sub y part. And following the sign convention that we know, this one gonna be V sub A part also. You can compute V sub A part. Okay, V sub A part gonna be negative of A sub y. This is what? This is going to be the slope theta A. Okay, and also over here, if you cut it over here, you will get this one for B sub y. Following the sign convention, okay, this one gonna be V sub B part. Now, when you get V sub B part, okay, this is gonna be equal to B sub y. It's gonna be what? It's gonna be this theta sub B. Okay, you can do that. Now, you can cut the beam at any length, okay? And then if you cut the beam for a given x from here to here, and then what you have what? The elastic weight is going to have this upward direction. This is positive. Okay, I said that's going to be opposite to W. W downward positive. So M sub EI upward positive. And then you have this one for A sub y part. When you cut this one with the X, you also have the same sign convention. This is gonna be M part. Okay, and this is gonna be V part. You again can use the equilibrium equation compute for the V part. It's gonna be theta at X. That means you will get the equation for the slope. Okay, that's going to be summation of f sub y equal to 0. If you take the moment over here, summation of the moment equal to 0, you will get m part. That's going to be the diffraction equation. Okay, if you use that one to plot the graph for this one, you will get the shear diagram of the conjugate beam like this one. Every point, okay, that's on this conjugate beam. You get what? You get the deflection. And then over here, shear is 0. That means slope is 0. This is going to be the point over here. As you know, this is symmetry. This point theta equal to 0. Okay, and then again, as you know, this is what? This is theta A. This is what? This is theta B. This is negative because the rotation like this one negative. Okay, this is positive, this one downward. Okay, this is going to be counterclockwise direction. Okay, and then they are in opposite. Okay, this one clockwise over here, this one counter clockwise over here. The same value, but different sign. Okay, and then I should say the theta has the unit of radian. Now, if you use this equation for the graph, you will get the form of this graph. Okay, and you can see the moment diagram of the conjugate beam over here is what? Is the same as the dashed line on the real beam. Okay, and this point is what? Have the value of 0. Okay, and this point of what? This point has the value of 0. That means V sub B equal to 0. But theta sub B won't be 0. Theta sub B is going to be here. theta sub B gonna be it. So based on of this consideration, Professor Otto said we have two theorems. Okay, the first theorem, the slope at a given point on the real beam equal to the shear force at that point on the conjugate beam. Okay, again, it's going to be this one, slope on the real beam equivalent to the shear force on this conjugate beam. And the second theorem, the deflection at a given point, on the real beam, this equation is going to be equivalent to the impact that's at that point on the conjugate beam. Okay, just remember the step. First, you get the beam, find the reaction. Okay. Second, draw the shear diagram of the real beam. Third, draw the moment diagram of the real beam. Okay. Then fourth, change M diagram to M over EI. Change it to elastic weight. Okay. And what? And draw the conjugate beam. Okay, draw the conjugate beam. And then what? Fifth, you compute. You may come over here. Okay, you compute for what? For V palm sub X for this one. And what? And M palm sub X for the deflection. Now, the last one, you may say, okay, you just draw the elastic curve with what? Elastic curve with slope and deflection. Now, all this kind of the concept, let me translate the concept into the practice. The first problem I'm introduce you going to be the easiest one. Okay, let's move your guys to this problem first. Why I can start with this one? This is unsymmetric beam. Okay, the elastic curve of this beam gonna be what? With the theta sub A smaller than theta sub B. Why I can know that? Because based on this picture, if you have the basic of engineering static, you will see the force B sub y gonna be larger than the force A sub y. If you want to believe it, take your ruler, okay, and then bend it, okay, bend it. If you bend it, you see 16 kilonewton close to the point B. So the slope at this point B gonna be larger than at this point A. Now, based on that one, you may draw the elastic curve of this one with a very good shape. And then again, you may put more detail on this one. If you get this one, this is going to be your elastic curve. This is going to be your theta A. Okay, and also following this one, this is going to be your theta B, and theta B is going to be larger than theta A. Okay, following this one is said the steel beam. Okay, this one has the W section has a constant fractional rigidity. So EI is going to be constant and then subjected to 16 kilonewton. The beam have the length total of 4, 6, 8, and then you should have the beam like this one. This is 7, and then half of this one. You will get the deflection over here to be the deflection at L over 2. Okay, and then following this one again, there is a point of maximum deflection occur about this one due to the unsymmetric beam. And this point is what? Theta gonna be 0. And this is going to be what's so called V max. Now, the problem asking you to determine V max. The problem asking you to determine the deflection SL over 2. And also asking you to determine the deflection at C. Okay. And also the slope at A, slope at B, and over here is going to be the slope at C. Okay. When you measure the slope, you measure it with respect to the tangential line and the horizontal line. For this one, due to the continuity of the beam at point C, you will get this one to be theta sub C equal if you measure on the left or you measure it on the right. Okay. Now, coming to the concept of the conjugate beam. Okay. The conjugate beam, very first one, you got to accept the first theorem. You got to draw the moment diagram of what? Of layout beam. And then you should convert this moment diagram, okay, into what? Into the M over EI, or it's going to be the elastic weight, okay. And following this one is not enough. Actually, I didn't put it yet. You got to draw the conjugate beam, okay, conjugate beam. The process of drawing the conjugate beam involves the drawing of the beam and also about the support. Okay, I should say about the support. Okay, we have the support of what? Support of the real beam and the support of the conjugate beam. Okay, you have what? You have pin at A. Okay, at A you have pin. Okay, at pin at A. Over here we have V sub A equal to 0, and we have what? Theta sub A won't be 0. By this consideration, what's gonna occur in the conjugate beam? On the conjugate beam due to this one, the what? The beam, when you draw this one, the slope, sorry, this one going to be the deflection is slope is equal to 0. So V sub prime, sorry, M sub prime A is gonna be 0. This is going to be second theorem. Okay, and then following this one, we have V sub prime A won't be 0. What kind of reaction on conjugate beam that has 0 moment and shear? Okay, again for this one at point A, you will get the shear. The shear force of what? Of A sub Y. Okay. And then you will get what? You will get this one to be 0. That means what? The pin is going to be the same pin on the conjugate beam. Okay, so you're going to draw the conjugate beam with the 7 meter. Sorry, 8 meter. 7 centimeter. This is gonna change to A palm, and this is gonna change to B palm. B palm, A palm. Sorry, you draw the conjugate beam over here. Okay, A palm and B palm. With what? With the support at A gonna be the same as the pin. Okay, and I should say in the reality, the external pin. The external pin on the real beam. It's going to be the external pin on the conjugate beam. Okay, this is our first consideration. Now, let me move to this point. This is what? This is roller. The same thing. V sub B equal to 0. No deflection at B. Boundary condition. And then theta sub B over here won't be 0. What happened here? Basis upon this one, the second theory, M sub B prime gonna be 0. Okay, and then we have what? We have V sub B prime won't be 0. That's gonna be B sub Y. Okay, so the external roller gonna keep it to be external roller on the conjugate beam. So keep it the same. Okay, now coming to the point, you got to draw the moment diagram and change it to the elastic weight act upon this one. Now, we first, you may say, okay, you may say, just analyze the beam, just the beam for reaction, shear diagram, and moment diagram. If you like to combine first, second, and third step from our previous discussion together, you may just like this one. It's gonna be 3 steps from the previous slides. Okay, based on this one, free body diagram of the beam. Okay, you may say free body diagram of the beam from free body diagram beam. Taking the moment is up to you. You may set just summation of the moment at point B equal to 0. Then the rotation of A sub Y gonna be in counterclockwise and A sub Y. You have A sub Y. A sub Y times 8 A sub Y. Rotate in this direction equal to 16 and then times 2. Okay, basis upon this one, A sub Y will be 16 times 2 divided by 8. You cut, this is 2. That's going to be 4 kilonewton. So this is going to be 4 kilonewton. Okay, now you move a bit to the second one, summation of F sub Y equal to 0. Summation of F sub Y equal to 0. Upward is positive. So B sub Y plus upward 4. And then that's going to be equal to 16. What you get is going to be B sub Y equal to 16 minus 4. That's going to be 12 kilonewton. This is 12 kilonewton. Okay. Now, you are ready to draw the shear diagram and moment diagram. Where is my pencil? Oh, okay, over here. You just draw it. As you may know from the ending static, for this one, it's going to be very easy. Take this one x meter, and take this one for the shear in kilonewton, and you have A sub Y over here to be 4 kilonewton. Just put it into 4 millimeter. Okay, if you say this is upward of this one plus 4. And then doing this one, W is 0. So dV by dx is 0. This one will be plus 4 up until this point, plus 4. Okay. And then 16, take downward. You just take this one for 16. Okay. You got minus 16 plus 4. This is minus 12. Then you have W equal to 0, dV by dx equal to 0. This is going to be minus 12. And then you have 12 up. Okay, so proceed. Now, if you draw shear diagram wrong, the moment diagram will be wrong. Okay, so take your knowledge and put it into practice. Then A is pin. Okay, A is pin. And also B is roller. This is kilonewton meter. This is X meter. You guys will know that the moment over here gonna be 0, and for sure the moment over here gonna be 0. No external moment. Then here over here is 4. dm by dx equal to plus 4. This one gonna go upward, and then m at this point C, at this point C, at this point C, this point C minus 0 equal to the area of the shear diagram. Okay, the area of the shear diagram gonna be over here. It's gonna be 4. This is 2. This is 4. This is gonna be 6 meters. So 4 times 6, and then you get m sub c equal to 24 kilonewton meter. Okay, taking this one, what you have, let's just take it to be 12 millimeter. Okay, just put it over here, and this is gonna be 24, and line gonna be like this one. This slope positive for plus 4. Then moving this one, dm by dx gonna be minus 12, and for sure you just draw the line link between them, because this is 0 due to the roller over here, and show you understanding the slope is gonna be something like this. Now you are ready to what? To what? To the second step. Okay, you may just say analyze the conjugate beam. Okay, the conjugate beam. Conjugate beam. And analyze for the reaction, okay, and then you may analyze for v sub x, and then you analyze for m sub x, and you know that this is going to be v prime, this is going to be m prime. Put the prime for the conjugate beam. Okay, and then you will see this equivalent to theta sub x, and this gonna equivalent to deflection v sub x. Based on this one, to draw the conjugate beam, and m over ei, I should say. By putting this one, this is gonna be 24, but it's gonna be 24 divided by ei. Okay, it's gonna be the moment divided by fractional rigidity, and then you just draw the same pictures over here, and then you can determine what the direction of m over ei. I said the downward is positive. Okay, so this is going to be in the upward. Okay, and then I should say the m over ei, okay, always point out of the conjugate beam. This is important. Always point out. If it's negative, it's point downward. If it's positive, it's point upward. Okay, now you have this one. You are ready to analyze the conjugate beam. Before you can do so, you got to do what? Determine the reaction. Okay, let me move. Okay, so based on this one, you guys will have the conjugate beam, and you should determine the reaction. Okay, let me put it into the free body diagram, and this is going to be your upward elastic weight, and then this is going to be the force of A sub y palm, and this is going to be the force of B sub y palm, and I should say this is going to be 2 meter, 2 meter. This is 6 meter. Now, from free body diagram of the conjugate beam, okay, the conjugate beam, we can determine the reaction. So the elastic weight is in the form of what? Triangular. Okay, and then following this one, you should say the load here should have the resultant force like this one, and this one also have this kind of resultant force, and then this is for this triangular area 1/2 of what? 24 over EI, and then time 2. Okay, and this one is going to be 24 over EI for this resultant force, and it at what? At the centroid of this area. Okay, since it's at the centroid of this area, this is going to be what? 2, right? So this is going to be 2 over 3, and this is going to be 2 times 2 over 3, going to be 4 over 3. One is the L, 2 divided by 3. Another one is 2/3 of the L. Okay, it's going to be 4. Then for this one, you have what? You have 1/2 of 6, and this is 24 over EI. Then this one going to be cut 3 times 24. It's going to be 72 over EI. Okay, and then the distance over here, from here to here, is going to be 2 meters. And this distance from here to here is going to be 4 meters. 6 over 3. Okay, L, the length, L over 3. And then 2L over 3. Now, taking the summation of the moment about what? About whatsoever, if you take about A palm equal to 0. Now, B sub y palm rotate in this direction positive. And this is going to be 8 palm B sub y palm rotate in this direction. I got to stop. Time out. Okay. Time out. Let me stop it first. Let us come back. Take the moment about what? About point A. This rotate in this direction. And then you have this one. Okay. Equal to 72 over EI. And this is 4 meters from A palm 4. Rotate in the opposite direction. Take on the right side. And then plus 24 over EI. Now, it's going to be what? The distance from my pen to A palm is be what? 6 plus 2/3. Okay, 6 plus 2/3. 6 is here. Plus 2/3 is over here. Right? So you got B sub y palm. Just do the combination of this one. You should get this one to be equal to 56 over EI. Okay. And this is going to be what? Equivalent to theta sub B. And since you know its rotation in this one, okay, just put it over here. And you just said this is 56 over EI. Just put it 56 over EI in this location. Okay, so you get the first answer. Then do the second one. Summation of f sub y equal to 0 downward is positive. This is downward. You get this one to be 56 over EI. And then a sub y prime plus 56 over EI. And then it's going to be equal to this one, 72 over EI in the opposite direction. And then plus 24 over EI. Okay, you will get a sub y prime very easy. This one plus 24 minus 56, you will get, I get 40. Okay, 40 over EI. This one is going to be 40 over EI. And this is going to be equivalent to theta sub A. And 40 over EI is going to be what? It's going to be over here. Okay, 40 over EI. Rotate in this direction. 40 over EI. Now you have two of that one already. This is going to be 56 over EI. And then 56 over EI larger than, as I show you, theta sub B larger than theta sub A. Now, let us move to slope theta sub C and V sub C. Okay. The C is what? C is over here. This is going to be C prime. Okay. And then the deflection from A prime to C prime. Okay, it's going to be the deflection from here to here. Okay, and that's going to relate to what? That's going to relate to this portion. Let me show you guys the whole thing. Okay, and then following these two, you got to determine the deflection at V over L over 2 and the deflection at point C, this one and this one. Okay, you are looking for this one. That means you're going to find what? The moment, okay, of conjugate beam at what? At this 2 points. So you may project it down over here. Okay, you may determine the moment over here. You may determine the moment M sub C prime. Okay, M sub C prime gonna be what? Gonna be this one, V sub C, and M prime L over 2. That's gonna be deflection over here. And if you like to determine the slope over here, you determine V prime sub C. Okay, V prime sub C also. So based upon this one, you may what? You determine 2 points at this one, at x equal to what? From here to here. It's going to be Sx equal to 4 meters. And this one, Sx equal to 6 meters. If you cut it, you got to cut 2 times. Okay, I don't like it. Okay, by doing this one, Ajahn will cut it any point here. And let me put it in the distance of x. Okay, let me cut it at a distance of x. And I said this is going to be x measure from the left to the right. Okay, and then I have what? I have this type of A sub y prime. And this is going to be 40 over EI. And then following this one, measure from here to here is 6 millimeter. Just put it about 6 millimeter. So you have the elastic weight for this given, okay, this given x. Now let me move you up over here. You cut it at x. What happened, kid? At this point, you will get the moment over here, m time of conjugate beam. That's going to be equivalent to the deflection at any x. Okay, and then you also will get this one from sine convention v time, and this is going to be equivalent to slope at any given x4 meter, x6 meter. It's up to you. Okay, now if you go to my own previous video clip, I didn't show like this one. Okay, I just cut it to time. That takes too much time. It's better to take it at x. Okay, and then later just cut x equal to 4, x equal to 6 to determine the required value of slope and deflection. So from the body diagram of the segment of the conjugate beam. In short, just put it like this one. Okay. Now you can do what? You can do summation of f sub y equal to 0, and this is downward. Just put it downward, positive v half. Okay, and then this is downward plus 40 over EI. Okay, and then you get what? Equal to this resultant force. Okay, can you determine this resultant force? Not yet. You got to know this value. You got to know this one. Okay, so this is 24 divided by 6. Okay, 24 divided by 6, the slope, 24 divided by 6. Let's put this one to be m. Okay, to be m, to be x, to be x. Okay, y. Okay, supposed to be y. This is equal to y. This is y divided by this tan of x. So you have y equal to 24x divided by 6. Okay, it's gonna be what? It's gonna be 4x. Okay, and this 4x must be divided by EI. So over here gonna be 4x divided by EI. 4x divided by n. And this one will be 1/2 times x and 4x over EI. And this one is going to be cut 2x squared over EI. Okay, it's going to be 2x squared over EI. And this is going to be x over 3. And this tan is going to be 2x over 3. Okay, now equal to this one equal to 2x squared divided by EI. Okay, you will have this equation easily. V half equal to 2x squared divided by EI minus 40 over EI. Okay, and this is gonna be equivalent to what? Equivalent to theta sub x. This is going to be the slope. Okay, and x can be what? From A to C. 0 less than equal to x. X less than equal to 6 meters. This equation only can be used in this yellow region. Okay, now when you finish this one, we take this one to zoom out, and then we have what? We have slope theta sub A. Now, if you guys just take point A, point A is what? Point A is x equal to 0. Take x equal to 0. This is going to be 40 over EI. the same as theta sub A. Okay, the same as theta sub A. Okay, if you prefer to determine the slope at this one, okay, at this one, if you prefer to, this is going to be theta at L over 2. This is going to be x equal to 4 meters. So if you like to determine that one, theta SL over 2 is going to be 2. Take 4 meters, put it over here. 4 square divided by EI minus 40 over EI. What did you get? This is 16 times 2 going to be 32. That's going to be minus 8 over EI. This is going to be 8 over EI. The rotation going to be the same as theta sub A. The rotation going to be in this direction. Okay. Now, the problem asks you to determine theta at C. Theta at C. C is what? C is going to be x equal to 6 meters. Then this is going to be 2 times 6 square divided by EI and minus 40 over EI. You get 32 times 2, 64. That's going to be 24 over EI. This is positive. Going to have opposite rotation to the slope over here. Okay. Now, let me take this one, 24 over EI over here. This is 24 over EI. The rotation opposite to this one, since it is positive. So this one gonna rotate in the same like this one. Okay. And then you're gonna move on to determine the deflection at C, at L over 2, at this one, maximum. At maximum, slope equal to 0. Okay. Now, let me move to determine the deflection. We got to determine M palm. Okay, following this one, we looking for M palm over here. Summation of the moment equal to 0. M palm rotate counterclockwise to be positive. So take the moment over here. You get what? You get M palm now. M palm rotate like this one. And then you can see 40 over EI rotate in the same direction plus 40 over EI times X. Then it's going to be equal to this one, 2x square over EI times this one, x over 3. Okay, x over 3. Now, rewrite it. Okay, rewrite it. This M palm gonna be equal to, this is gonna be 2x cubed over 3 EI. Okay. Which one? This one 40 times x and this one x squared times that's theta sub c. This is 36 6 square 36 times 2 72. Okay, 72 minus 40. Thank you. It's going to be what? 32. Thank you. Change this one to 32. Okay. Yeah, that's going to be exactly. We get this one, 32. But I approach the solution to this one. This is different. Thank you very much for for this one. Another one, this one is correct, right? 16 half to 32 minus 48. Now, let me move to m prime. Okay, m prime over here gonna be 2x cubed over 3i, and then minus 40x over ei, and this one gonna be equivalent to v sub x. Okay, this is equivalent to v sub x. Now, if you like to find the deflection at point C, x equal to 6 meter. So x equal to 6 meter, v sub c equal to 2/3 ei, and this is going to be 6 power 3 minus 40 times 6 over ei. Okay, you should get this one for what? V sub c. 9. Take your calculator. 6. What do you get? It's going to be negative 96 divided by ei. Okay, and then it's going to be 96 over ei with the downward. Okay, this is negative. So you may take it over here, 96 over ei and downward. Okay. Now for v, oh, this is wrong. This is v over. This is 96 over ei downward. Okay. Now at x equal to L over 2, this is 4 meter. So we have v at L over 2. Take this equation 2/3 and 4 cubed divided by ei minus 40x over ei, and then you should get the result of this one to be negative something divided by ei. What did you get? What did you get? $42.67 minus this is times 4, okay, minus 160. I got it to be minus 117.33. Okay, you may say this is going to be 117.33 over ei and then downward. Okay, right? You get the same number, right? Okay, that is going to be 117.33 over ei. You can see the deflection, the red one over here, larger than this blue one. Okay, a bit larger, 117.33 and 96. Okay, this is 96. This is 117.33. Now, this is Vmax. Okay, how can find Vmax? You got to use this property. The shear must be 0 over there. Okay, now you come to this equation, and then you got to find V max. Okay, to find V max. V prime equivalent to theta equal to 0. So this equation is 2x squared divided by ei, and then it's gonna be equal to 40 over ei cut. So you will get x equal to 40 divided by 2, and then square root of, you got square root 20. That's gonna be 4.5 0.472 meter. This is the location for Vmax. Okay, so just take it. This is 4 meter. This is 4.472. This is 6. So the maximum going to be between L over 2 and C. Okay, and then we have V max equivalent to M max, and then take this one to third, and then divided by EI 4.472, and then Q minus 40 times 4.472 divided by EI. And then you should get minus 119.26 over EI. It's going to be 119.26 over EI, and then downward. Okay, and then downward. And then over here, just take this one. 119.26 over EI, and then downward. Now, if Ajahn provide you with the EI, okay, EI is going to be 100,000, okay, and then unit going to be kilonewton per square meter times meter power 4. Okay, if you like to, let me put it to 1 million. Okay, 1 million. So this is going to be what? This is going to be 40 10 minus 6 radian. Okay, rotate in this direction. EI must be divided, and then the slope must be in the units of radian. And this is going to be what? 56 10 minus 6 radian in this direction. And this is going to be 96 10 minus 6 meter. Meter. It's going to be what? It's going to be equivalent to what? 0.096 millimeter downward. Very small. Okay, the same. You can compute for the other thing. That's the first example. Okay, to show you guys how to solve this kind of beam basis upon the conjugate beam. And I should say, okay, if you go, I should say, this equation can be checked with what you have from the deflection table. And if you go to what we have, the cover of this one gone, you may determine the equation. Okay, go to the deflection table. The deflection that we have in this yellow, okay, the equation of this one is going to be V equal to minus PBX over 6 EIL over 6 EIL, and then time L squared minus B squared minus X squared. Okay, if you take it from the deflection table. Now, take this one to be minus 16. Okay, and this is going to be A. A is going to be 6 meter. B is going to be 2 meter times 2. And then X. And then divided by 6 EI. And then L going to be 8. Okay. And in this one, 8 squared minus 2 squared minus X squared. If you put it, okay, you will get this one to be minus 2x over 3ei, and over here going to be 60 minus x squared, and the result you have here is going to be the same as the result over here. Okay, if you times 60 with 2 divided by 3, you're going to get 40. And then you take this one out, you will get this term. Okay, and that's proof what we have for conjugate beam with the deflection table. That's get from what? From double integration method. Okay, every method provide the same result. Okay, let me stop on this one first. After we finish this discussion, we consider the simple beam, right? And we have another type of beam, such as what? Such as cantilever beam. Ajahn already provide you guys with the cantilever beam and overhang beam. There are two more types of it for our study. Okay, let me take you guys over here. You can review every detail of this one. I will come back later for this one. Maybe next lecture. Before we limited time, due to our limited time, let me talking about the conjugate beam support. Okay, we have the cantilever beam over here. Okay, this is the real beam. Okay, this one is the real beam. Under the application of the point load at the end of it, we have what? We have the elastic curve. This is fixed end. Okay, fixed end of what? V sub ay equal to 0, theta a equal to 0. And then when it's subjected to the force, take your ruler, put the force. Okay, you get what? You get the deflection. You get the elastic curve. Now, you get the elastic curve. And then the value of the deflection and the value of the slope gonna change with the this tan x. Okay, so I said the deflection is the function of x and slope also function of x. Fa is what? Fa x equal to 0. Okay, so basis upon this one, we have the real beam. Okay, and then for this one, x equal to L, we have what? We have V sub C and also we have theta sub C. Now, to consider it as the conjugate beam, we take the beam over here. We consider the boundary condition of the beam. When this have the value won't be 0. That means over here we have M palm sub C palm. Okay, since this one would be 0, over here at point C palm, we have V palm sub C palm. When we talking about at point A, this change to A palm. When we talking about this one, okay, this one, V palm sub A palm equal to 0. This is 0. This is 0. Conjugate beam. This is what? This won't be 0. This one won't be 0. Okay. This one 0. It means what? It means this one corresponding to M palm, A palm to be 0. Now, taking a consideration over here, free end. Okay. Over here is free end. Okay. Free end is what? Free end has moment equal to 0. Okay. Free end has the moment equal to 0. And then free end actually have the shear. Okay. If have P equal to 0, this one gonna be 0. What we have in this consideration about the boundary condition. We have this one corresponding to this one, the slope corresponding to this one. This is fixed end of the real beam is going to change to the point of zero shear and zero moment. You got to change fixed end to be the free end. Okay, and at this point, this one corresponding to this one corresponding to this one. Any point that has the moment and the shear, you got to change free end to be the fixed end. Okay, so this principle of consider of the boundary condition, as I discussed, fixed end change to free end, and then free end change to fixed end by this even lesson. Now, let me move you to the comparison. Fixed, okay, change to free. Why? Because the real beam have zero slope. Free end V palm equal to zero. Fixed end have zero deflection. M palm of free end equal to zero. And then free change to fixed. Okay. If you understand it, remember fixed to free, free to fixed. Okay. And then pin and roller, as I discussed before, this one theta won't be zero, V palm won't be zero. However, this is zero, M palm to be zero. The support that has shear and zero moment gonna be roller and pin, external pin and external roller. I should say external pin and external roller gonna be the same. Now, coming to a more complicated one, the hinge. Okay, the hinge can move downward with different slope. Okay, move this one. So slope won't be zero, and then deflection won't be zero. What happened on this one? V palm won't be zero, M palm won't be zero. Internal hinge change to internal roller and also internal pin if you prefer, because shear force over here is not zero, moment over here is not zero, corresponding to the reasoning that given here. Now, internal support over here, we have what? Slope won't be zero. Okay, deflection equal to zero. That means V palm won't be zero, and deflection M palm equal to zero. That's gonna change to internal hinge. The hinge over here has no moment resistance. Okay. Now remember it. Fix change to free. Free change to fix. External pin, external roller, the same. Internal hinge change to internal roller. Okay. Internal roller change to internal hinge. Okay. Now we review it. This external pin, external roller, the conjugate beam gonna be the same. Okay. This is fixed change to free. This is free change to fixed. Like this one. This gonna be the same. Okay. This gonna change to fixed. Free change to fixed. And this gonna change to internal hinge. Internal hinge and fixed. And then this gonna be the same. This one change to internal hinge. This one change to free. So roller, internal hinge, and free. Roller, internal hinge and free. Okay. This one change to free. Internal roller, and free. This one may be internal hinge, internal roller, or up to you. Okay. Then this one the same. Okay. Change this one to internal hinge. Change this one to internal roller. This one the same. Okay. The same. Internal roller, internal hinge, change to internal roller. The same. Okay. These two change to internal hinge. Okay, like this one. And then free. Internal hinge, free. Internal hinge, free. And then free. Again, these two conjugate beam gonna be in equilibrium. Don't worry. Elastic weight will balance itself. Okay. And then coming to the other thing. Fix, change to free. And free, change to fix. Fix, change to free. And this one gonna be free. Okay. And this one gonna be the same. This one, the same. And this one change to internal hinge. This one, the same. This one change to internal hinge. And this one gonna be fixed. Okay. And free, internal roller, free. And then the same. And then internal hinge. Internal roller, internal hinge, and then the same. Okay, you go back and do the practice on this. Okay, now I come to the last example. Let me, for this lecture, we're going to come back next time with more example, a more complicated one. Now, let me move you to the cantilever beam. Let me move you to the cantilever beam. Up. This one gonna use the concept that we just discussed on this problem. The beam is gonna be cantilever beam. And this one subjected to 10 kilonewton. Okay. And also the external moment of 50 kilonewton meter. And following this one, the beam have constant EI. And the conjugate beam is used to determine the slope at B and the deflection at B. And for sure, you guys should be able to draw the elastic curve. Okay, it's supposed to be something like this one. Due to the fixed end, no movement. Okay, and then due to the free end, this one supposed to move downward. Let me put it over here. And then just draw the elastic curve. If you prefer, just bend your protector ruler and draw the line. Okay, link between the point. Okay, this is going to be your very beautiful elastic curve if you can bend it and draw it. And this is going to be V sub B. Okay, this is going to be V sub B. And then for the slope, reference to the same horizontal line over here, positive X. Then tangential line going to be here. This is going to be the slope theta B. This is going to be the slope theta B from your elastic curve. Now, what should we do? Again, we come to the concept of conjugate beam. On the conjugate beam, as I discussed before, you got to what? You got to draw the moment diagram. Okay. On the moment diagram, then you just change it to be the elastic weight. This one gonna be EIGHT. Okay, and then we have what? We got to the conjugate. Let me put it in short. Okay, conjugate beam. Now, following the same step as before, the first one, you guys got to analyze the real beam. Okay, analyze the real beam for reactions, shear diagram, and moment diagram. Okay, if you do it wrong, everything gonna be wrong. Now, following this one, you supposed to have this A sub y, and for sure you're gonna have this one to be M sub A. Now, from free body diagram of the beam, we have what? Summation of x sub x equal to 0. If you prefer, you should have A sub x over here to be 0. And then also summation of f sub y to be 0. Upward is positive. A sub y gonna be 10 kilonewton. Okay, 10 kilonewton. This one gonna be 10 kilonewton. And summation moment about A equal to 0. Take moment over here. This rotation is positive. M sub A. Rotate in this way. We have this one downward. This one downward equal to 10 times the distance 10 and then plus 50. Okay, so you should get the reaction over moment over here to be 150 kilonewton meter. So this is 150 kilonewton meters. Now, the same as before, draw the shear diagram and moment diagram. Okay, just take this one and then you have this is x meter and then this is going to be your V in kilonewton and this is 0, 5 and 10 meter. If you prefer, just put it like this one. Upward shear, okay, of 10 kilonewton. So just put it 5 millimeter, say upward. And then this is plus 10. W again is 0. Next time I will calculate, analyze the beam with the load W. This one, W is 0, is easy. dV by dx equal to 0. Constant slope. And then constant value of this one plus 10 and then downward. Okay. Then we have what the same x meter and 0, 5, 10. The axis now change to the moment in order to draw the moment diagram. M kilonewton meter. 150 counter clockwise. That means negative. Okay, so for this one, you get this one for 15 millimeter, and you set this one minus 150. And then we have this is positive 10. So dm by dx is going to be plus 10. And what's going to be the moment over here? M sub b over here minus 150 and it's going to be equal to the area equal to 10 times 10. So M sub b is going to be 100. This change to positive. Move this one to be negative. So this is minus 50 kilonewton meter. That's gonna be 5 millimeter over here, and the value is gonna be minus 50, and then you have this one. Now, this is what clockwise, so it's take this one upward to positive. This one take negative downward. Now, you got to go to the second one, draw the conjugate beam. You draw the conjugate beam, okay, and analyze it, okay, to determine reaction V sub x and M sub x. Okay. Now you are gonna use the concept fix change to free change to fix. Okay, the conjugate beam is here. Point A change to A palm. Point B change to B palm. The fix change to free. The free change to fix. So this is gonna be the conjugate beam. Okay. The elastic weight, the same thing. Take this one, 150. This is gonna be 50. And I should say M over EI. Okay. M over EI have the way to point out of the conjugate beam. Always point out of the conjugate beam. Then you have the elastic weight for this one to be something like this one. And then this is 150 over EI. No negative sign. No negative sign. Okay, this is going to be 50 over EI. Okay. Now we move to determine the reaction. The same thing. Just the free body diagram. Okay. And then we have this one for 50 over EI. And this one for 150 over EI. And then we have this one. Okay. What we have is the reaction. That's going to be over here. That's going to be over here. This one going to be B sub Y. And then for the moment, since elastic weight rotate on this one, you have this one to be M sub B. Okay. And you should say that M sub B is going to be equivalent to what? M sub B gonna equivalent to what? From this pictures, M sub B gonna equivalent to V sub B. Definite B. Okay. And then for this one, B sub Y equivalent to zeta sub B. So this one, you don't need to determine these two equations. You get the reaction. And direction going to be the shear and the moment, okay, at that point. Now, following this one, summation F sub Y equal to 0 should be upward is positive. Okay. Ajahn, you tell me, you got to use the sign convention. You may use the sign convention also. If you cut it over here, okay, if you cut it over here, you will get this one to be B sub Y. Okay, you will get this one to be M sub B. Then the internal force over here, you will have this one to be V sub B palm. Okay, this is going to be your result. And this one is also going to be your M sub B palm. The value is going to be the same. Only the direction change. Okay, so don't worry. And then we will get the direction for what? For the elastic curve. Don't involve with this sign convention. Okay, You got to mess up. Now, following this one, upward, B sub Y. This one upward. Now this one separate into two portion. Okay. The first one for this one, is has the value over here of 50 over EI. And for sure, okay, this gonna provide the resultant force of what? 50 over EI times the length over here of 10 meter of 10. So this one should be provided with 500 over EI. Oh, sorry, in this direction, in this downward direction. This downward direction is not upward, downward direction. And then what? Another one, you have triangle. Okay, for this one, you have this resultant force of what? 1/2. Now, this is what? This is what? 100. Okay, this is going to be 100 over EI. And then times 10. Cut to 5. This is going to be 500 over EI. And then you should say, okay, this one will separate into 5 meter and 5 meter. This one will separate into 10 over 3 and 20 over 3 meter. Now, let me move you guys over here. This B sub Y upward, and then it's going to be equal to 500 over EI. And this one plus 500 over EI. So your B sub Y going to be 1000 over EI. Okay. And then the rotation go up over here. Okay. You have this type of rotation. Okay. If EI is a million, again, if EI is going to be million kilonewton per square meter times meter power 4. This one is going to be what? It's going to be 10 minus 3 radian in this direction. Okay. 10 power 3 divided by 10 power 6. 10 minus 3. Now, summation of the moment about this one, B palm. Okay, B palm equal to 0. Take the moment over here. We have M sub B rotate in this direction equal to 500 over EI and times this one for 5 meter. And then you also have this one in opposite direction plus 500 over EI. And the distance from here to here is going to be 20 divided by 3. Okay, and then you should get the result. This is 2,500. This is going to be 10,000 divided by 3. So you have this one to be 1,750 divided by 3 EI. And this one for sure, in the direction of this one, is going to be downward. And again, this one going to be 1,750 divided by 3. It's going to be what? 5833.3. Okay, and this is going to be 5833.3 over EI, and then 10 minus 6. So you will get this one to be 5.8323, 10 minus 3 meter and downward. That's about 5.83 millimeter. This is 5.83 83 millimeter downward. Okay, and that's going to be another important example. There are much more things to consider by the conjugate beam since it is very powerful. But I should say, when the load is point load, when the load is going to be the couple moment, the calculation going to be easy. But if the beam subjected to uniformly distributed load, now require mathematics, okay, skill to solve it. But don't worry, all of you guys have very good mathematics skill. You are engineer student, okay? In student, you got to be very good technique. Now, for the PowerPoint, okay, we mentioned about the procedure. Ajahn did show you the procedure already, okay? And then following this one, we have a simple beam, but this one has 10 kilonewton force. I like you guys to go to the PowerPoint and review it. Okay, this the beam with the constant fractional rigidity. Now, after you finish review of this one, you also should go to the next one. I just checked the result, okay, of this one. Okay, this one also simple because it's subjected to couple moment. Ajahn can combine both couple moment and point load together. So the problem gonna be easy to do the calculation. But anyway, we got to show the example when the beam subjected to uniformly distributed load also. Okay, just have chance, just go to applicate. This thing, the conjugate beam is a bit tricky. Okay, the conjugate beam is a bit tricky. You can study it by yourself. Or if you prefer, you may go to my video clip. And you take my video clip and combine with this one easily. This one is more interesting. Because of what? This one have the section change at the middle. Sometimes we got to strengthening the structures. Okay. In the future, I think the repairing or strengthening or what so called rehabilitation. This kind of engineering work will come for sure because in the previous 50 years, we built a number of buildings. And since we use it for 50 years, you got to repair it. Something damage may occur in your structure, especially in the bridge, those kind of things. And to strengthening the structure, you may put the steel plate, okay, maybe on the bottom only, or maybe on both on the top and the bottom. Most of the time, they just put it on the bottom only. By putting this one, you increasing the stiffness, and strength of the beam. The beam can take more applied loading, and the beam will have, for a given loading, the beam will have smaller deflection. Okay, you don't need to take off and put a bigger one. You may just put the steel plate at the bottom because the maximum moment occur on this region more than the other region when you increase I. That means you increase the divider, the deflection gonna get smaller. Okay, the stress also because sigma equal to my over I. When you increase I, the stress gets smaller. Okay, that means it can take more load, more because the beam gonna have larger stiffness and larger strength. Okay, I will come back for this problem. I will come back on this problem. I also have a more interested problem. I should work on this one also. If I have time, next time I will have these two examples and also this one. I hope I can finish these three examples next time, and we will finish conjugate-beam. And that's going to be finish of our second problem, okay, in our third midterm examination. And then we move to the determine the deflection for the task and for the frame, for the third and fourth. And then when we finish it, we're supposed to have midterm examination on the week 11. Okay, and that's gonna be the lecture of today. Any question? Okay, no question. We finish it. Oh, you got to accept one thing. Chapter 8 require this kind of calculation. Okay, if you did wrong on chapter 7, okay, chapter 8 you will have big problem also. Okay, thank you very much.
The procedure of analysis. We're going to do what? We're going to start by analyzing the real beam to get the moment diagram, and we convert the moment diagram. The main thing is we're going to convert. Okay, we're going to convert the real beam into the conjugate beam. Okay, that's going to be what? That's going to involve with changing the support of the beam. Fix change to free, change to fix, pin, external roller, still the same, internal hinge, change to internal support, change to internal hinge, and then you also convert the moment diagram to the elastic weight. The elastic weight always have the direction that point out from the beam. Okay, it's going to point out, always point out from the beam. And then we do what? And then we do the opposite direction of the force. That is going to be in the blue line over here. That is going to be in opposite. That is point out. And analyze the conjugate beam. And you have two theorems. The V palm going to be the slope. Okay, the M palm going to be the deflection. V palm going to be the slope. Okay, and M palm going to be the deflection. And this is some useful pictures and equation that you may use if you like. Okay, let us consider some example. First one, we are going to determine the maximum deflection of this simple beam having the E of 200 gigapascal and I of this. What we have is, under application of the force, this beam gonna have large slope here and smaller slope here, and the deflection of this beam is going to be something like this. The maximum deflection will not occur at this half span of the beam. However, due to the application of the force that's on the AC side, so the maximum deflection should be here. So this is supposed to be the maximum deflection. What's important there, the maximum deflection is the same as the maximum of the function. The important here is the slope. Okay, at the maximum deflection, the slope is 0. Okay, when you determine this, it means that by the conjugate beam, V palm is 0. Okay, that is the important thing. And then we go by step by step. First, we analyze the real beam to get the bending moment. You may take the moment about B, and if you take the moment about B, what you get? This is going to be A sub Y. A sub Y going to times 4, so summation M sub A equal to 0. A sub Y times 4. A sub Y times 4 going to rotate this way, and then 10 going to rotate in the different direction, so it's equal to 10 times 3. So A sub Y going to be 30 times 4. That is going to be 7.5 kilonewton. So this is 7.5 kilonewton. So you do the summation of f sub y equal to 0. You got this for the b sub y. So the b sub y is up plus 7.5, and then this is downwards is 10. So what you get is what? B sub y gonna be 2.5 kilonewton. So this is gonna be 2.5 kilonewton. And then we're going to draw the shear diagram. Okay, when you do that, you got to use the ruler, not sketch at me. Okay, and I just show you to review you the knowledge of this. So the shear 7.5 going to pull it up this way. Okay, that's it's going to be plus 7.5. And since there is no W here, so the value of this is going to be constant because the slope is 0. And then when you arrive at the 10 kilonewton, they're going to take you down for 10. Okay, that is going to be plus 7.5 and minus of what? Minus of 10. So it's going to be minus 2.5. And then over here, there is no W. So slope is 0 and everything could be here. And then over here, there is 2.5 kilonewton. So it's close. That is the moment diagram. And then, sorry, that's a shear diagram. For the moment diagram, we are going here. The moment here is 0 because it's a pin with no external moment. This is also 0 because it's a roller. And what we have is, when we come over here, the slope here is going to be, sorry, the shear here is 7 plus 7.5. So the slope here is going to be plus 7.5. So it's going to be up steps like this, 7.5, 7.5, 7.5, 7.5, but up until here. And the moment here, minus over here, minus 0. Gonna be what? Gonna be this. This is gonna be equal to 7.5 times 1. So the M is going to be 7.5 kilonewton meter for this. And then the shear is minus 2. When the shear is minus 2, slope is going to be minus 2. And you know that's 2.5, sorry, 2.5. And you also know that this is going to have 0 moment. So the moment diagram of this is going to be something like this. Okay, that's what we have. Okay, and when you do the calculation, we will get the same thing as I just showed you. You got to convert this into the conjugate beam, and luckily, what we have is the real beam. The real beam we have the what? Pin and roller support. So when you change the real beam into the conjugate beam, the pin still the same. Change the A to A palm, and the roller still the same, and change the B to B palm. What's going to change? The moment diagram. That's going to change to elastic weight, and it's going to have the same shape. Okay, this is going to be 7.5 divided by EI. And the main thing is the direction of elastic weight always in the opposite direction of the load. So this one always point out of the beam. It's going to point out of the beam like this. And then we arrive at the real beam as shown here. Okay, you may take a look at your PowerPoint until you get what I'm showing you. And then we have the conjugate beam, the same one as I'm showing here. And next, when we have this, you're going to determine what? You're going to mean the A sub y palm and B sub y palm. And you also need to know that the A sub y palm going to be zeta sub A, and B sub y palm going to be zeta sub B, if you like to determine. So what we should like to do, you analyze the conjugate beam to determine the reaction. Okay, and then what you have is what? You're going to take the moment at B to determine the A sub y palm. That means the A sub y palm gonna rotate in the counterclockwise manner. So we put this one as positive. And what we have is this one gonna have this moment arm. That is gonna be R sub A palm. You may set R sub A palm, or you may like to take it a sub y prime whatsoever. Okay, and what we have is what we have the area here. Okay, and the area here gonna have the resultant force here, and this is going to be 1/2 with this is 1 meter times 1 meter and times 7.5 divided by EI. And how far away from B? If you take this, it's going to be from here to here. And what is going to be here? That is going to be 1/3 of the meter, right? That is 1 meter, and the centroid of the triangle is 1/3. So it's going to time 3 plus 1/3. That is going to be this area. And then we also have the what? Also have the resultant here. That is 1/2 of what? Of this 3 meter times 3 meter and times 7.5 divided by EI. So you got this. And the distance that's measured from here to here is going to be 2/3 of the base of 3. So you got this. Then you put everything in your calculator. You get this of what? Of 8.75 divided by EI. Okay, and that is going to be the slope at A. So the slope here, if you measure, it's going to be 8.75 divided by EI. And also, if you like to determine the slope at theta sub B, you got to take the moment this time about A, and the rotation of this is going to be in this direction. So I got this as the plus. Okay, that is going to be in clockwise direction. Just take this one up. Okay, and what we have is take moment about here B sub y. Let's me call it B sub y prime. Okay, B sub y prime times 4. And the author, this is 1/2 of 1.75, and put it in the okay, like bow. This is going to rotate about what? About A, and it's going to rotate this way, which is in opposite to the rotation of B sub y. So we got to measure from there to there. What we have is what? We have measure from here to here. This is 1/3 already, so this is going to be 2/3. So this is going to be here. And another one, the green one. The green one also trying to rotate this way. So we have the green one here. Oops, sorry, green one. This green one gonna have the distance of what? Gonna have the distance from here and measure to here. What we have is this is already 1 meter. So what left for here? This is 2/3 of 3. So this is gonna be 1/3 of 3. And then we have 1 plus 1/3 of 3 here. And then you put it, you get this as the theta sub B. And you may see that this theta sub B is what is smaller than that of theta sub A. Then we have this with this direction of 6.25 divided by EI. Okay, and what happened is the maximum deflection gonna occur here. Okay, with the what? With the deflection here reduced and the slope here of 0. So if we like to determine the location of Vmax, we need to find this x in which the theta sub x is going to be 0. So next we determine by cutting this portion, and then we have the B sub y prime is here. And what happened is, what is this? By similar triangle, we have this one divided by this one 3. So you have 7.5 divided EI. This is 7.5, and then is also divided by the x, and it's going to be equal to this is going to be the y, and then the distance here is going to be x, so it's equal to y divided by x, right? Oh, sorry, this is wrong. 7.5 divided by 3. Oops, it's not correct. That is wrong. Okay, this is wrong. This is gonna divided by 3. 7.5 divided by 3 equal to y divided by x. So you may rearrange this, and then you get this of 2.5x divided by EI. So what we have now is this. Okay, and when we have this, we also have v prime equal to 0. That is the point that we have focus about, in which the theta is 0. Okay, what is the area here? It's going to be 1/2 with the x times the 2.5x over EI. Okay, you make summation of f sub y equal to 0, and then you may have this one if the plus is upward. So v plus 1/2 of this, and then you may minus by this, and then this one equal to 0. You can solve for the x. X is 2.236. So now we arrive at the point that this one is going to be 2.236, and see, it's not the half of the midspan. Half of midspan could be 2. Is 4 divided by 2 is 2. Okay, okay, and then we have this. Now we can take the moment to determine the diffraction. Okay, with the Vmax, we got to take the moment here, and when you take the moment, summation of m prime equal to 0. What we have is the rotation here is positive. So if you may recall, you have this as the area. Okay, and this is going to be what? 1/2 of 2.236 and times this of 2.5 divided by EI and times x. This is going to be square. And what the location of it? The location of it is going to be here. That is going to be 2.236 divided by 3, right? And it's going to have the opposite of the impact. So we have this one, 1/2 of 2.5 times this. Okay, and this is what? This is the location of the centroid over here. And then we have what? We have this rotate in the same direction. So this is the plus, and this is the minus. And then what you get is delta prime equal to m prime equal to 9.317 with the minus sign. The minus sign indicates that it's going to be downward. Okay, negative sign. And then if you input the EI, since this is the kilonewton, so 210 power 9 Newton per square meter must change to 10 power 6. And then also millimeter power 4 need to change to meter power 4. And then you get it for 6.8 millimeter, and 6.8 is kind of small. Okay, it's produced the ratio of 588.3, which is larger than 260. So it's okay. Okay, that is our first example. And next we have the beam with the what? With the symmetry about point D. Okay, since it's subjected to the same moment, and they are asking us to determine the diffraction at point D of the beam. Okay, and giving us the E and the I. So we first determine the equation first, and then we put the E and I into the equation. Then first step, we're going to analyze this structure. And what we have, this structure going to be what? This structure going to subjected to only 18 kilonewton meter, and this is going to be 18 kilonewton meter, and we have the reaction over here, okay, only B sub y, and over here we have C sub y and also C sub x. If you do the summation of x sub x equal to 0, sure, C sub x equal to 0. Okay, if you summation of moment, let's take the moment at C equal to 0. What we have is what? B sub y gonna times this length of 6 meter. So we have 6b sub y, and it's gonna rotate this way. It's positive. So it's gonna plus 18 minus 18 equal to 0. So the b sub y is 0. There is no reaction force. And also, if you summation of f sub y equal to 0, c sub y plus 0 equal to 0. So there is no reaction occur at the pin and roller support. And then what's going to be the shear diagram? Okay, the shear diagram going to be this. Since there is no force, so the dv by dx is going to be 0. Okay, and from the condition that if the upward force delta v is positive and downward force delta v is negative, but this is no force, so it's 0 with the s equal to 0, and then this one going to be 0. And for the moment, what do you think when you move to the left? Which moment is what? Counterclockwise. Okay, the moment counterclockwise, if you consider it by following the sign convention, okay, you will see the m plus 18 equal to 0. So m equal to minus 18 kilonewton meter. So this one must be minus 18. Okay, and what happened is the dm by dx equal to v. So it's equal to 0. So no slope. Okay, so it's 0. And then it's alive here. We have this one for 18 kilonewton meter. So it's close to the diagram. Now, what it should be? We're going to change the real beam into the conjugate beam by doing this. Let's try to consider this one. What happens is the moment, okay, gonna divided by the EI, and you may take this one out, no sign, EI, and then since it's downward, okay, you take the sign out, and you may put this as the required direction of the elastic weight. So our elastic weight is 18 divided by EI. And next, what's going to be the support of this beam? The phi will change to fixed. Free end change to fixed. Internal support going to be internal hinge. Internal support going to be internal hinge. And you may see one thing, one important thing. What is? The beam is in symmetry. Okay, is symmetry. The left and the right are the same. So we convert the conjugate beam. Okay, fixed change to free change to fixed. Internal pin and roller change to internal hinge. And you may see due to the symmetry again. Okay, you may consider only this portion of the beam. Only this portion of the beam. And you may see that the V sub V palm and V sub C palm, they are going to be equal. Okay, and they are going to be zeta sub C, and they are going to be zeta sub V. Okay, before we can determine the deflection at D, okay, or the moment, this is going to be M sub D palm. We got to determine the shear first. So we can see that by symmetry, the elastic weight here, okay, will distribute to the left, and the elastic weight here gonna distribute to the right. And what is this? This is 3 meters. So This is 3 meter. And V sub C prime, if you like, is going to be 18 divided by EI and times 3. And then you can get this one for 52 divided by EI on both sides. Okay. And if you take the left portion, and then you can draw the free body diagram like this, and this is going to be M sub D prime. This is D prime. Okay. And you just do the summation of the moment. Summation of the moment. You may put this over here. Summation of the moment at what? At D prime equal to 0. By doing this, you have the M sub D prime in this direction. So this is M sub D prime. Okay, and you may get M sub D prime equal to what? M sub D prime equal to this one, 53 divided by EI, and you got to times this for 3 meter, and then you got this. This is also 18 EI, okay, and it's gonna time 3, and it's have this for 1.5, so it's have this one and time 1.5 with the rotation in which way? In this way, okay, opposite. So it's have that. What? This one is what? Oh, you take moment here. Sorry, take moment here. So you take this one out. Okay, this one gonna produce the force of 18 divided by I, and then times 3, and then it's going to rotate this way. Okay, it's the same this one of M sub D prime, so it's moved to the right hand side. It have negative here, and then we have this for 81 point divided by EI. That is going to be the deflection at D. Okay, and then you put it, you can get it for 3.24 millimeter upward. And then you may determine the deflection at slope at B. We have that, right? That is going to be 54 divided by EI. That is the slope at B. The slope at B. We determine the slope at B. Okay, that is going to be 54 divided by EI. How about the deflection SB? There is no deflection SB. That is 0. Slope at C. Slope at C is the same as slope SB. That is 54 divided by EI. And the deflection at A, is over here. Okay, if you like, you may writing the free body diagram here. Okay, and what you have the weight here of what? Of elastic weight here of 18 divided by EI. Okay, and you also have what? You also have the 54 divided by EI here. So this is upward. Okay, when it's come here, it's going to be down. Let me put this one. It's going to be downward of 54 divided by EI. So by doing this, we can determine the deflection at A. So this is M prime, and this is going to be V sub A prime and M sub A prime. By putting this, let me have this. What? That is going to be M sub A prime, and this is going to be V sub A prime, and this is going to be 4 meter. What we have is summation of F sub Y equal to 0. So up is plus. So what we have is V sub A prime, V sub A prime up. Okay, and minus 54 divided by EI, and also this one minus 18 divided by EI times 4 and equal to 0. You may put this into your calculator. That is 18 times 4 and then plus 54. That's 126. So V sub A prime equal to 126 divided by EI. That is going to be zeta sub A. And if you like, you may go further. Summation with Oh, sorry, this one, or A palm. Okay, A palm equal to 0. And then you have what? You have this as positive. So now M sub A palm is what? M sub A palm is positive M sub A palm. And this one gonna rotate the same way. So it's plus 54 divided by EI. And it's gonna time the distance of what? The distance of 4. Okay. And then what we have is this one. That's time 4. And then it's gonna time 2 here. So it's gonna be plus, right? They are going to plus what? Plus 18 divided by I times 4 and times 2 and then equal to 0. So you may get 18 times 4 and then times 2, that is 144. And 54 times 4 to 60 plus 144. That is going to be 360. M palm sub A is equal to minus 360 divided by EI. Okay, and then you get the result of this. And it's going to be what? Downward, right? It's going to be downward. This is, you may write this for the 360 divided by EI. And the direction of this, the negative set is going to be downward. Okay, that is the end of the second problem. And this third question is kind of a special one because the moment of inertia of the beam are not equal. Okay, this is going to affect what? This is going to affect the elastic weight, because elastic weight is going to be divided by EI. Okay, the beam is symmetry. So the beam is symmetry. So this A sub Y going to be easy to find. This B sub Y equal to 5 because the symmetry is the beam. So A sub Y is going to be 20 kilonewton. And B sub Y also 20 kilonewton. And the shear diagram, oh, very simple. The shear diagram going to be up for plus 20 and no distributed force. So S equal to 0. Get this one for 0. And up here, they take you down for 40. So it's going to be plus 20 minus 40. So it's going to be minus 20. And then there is no W. So this is S equal to 0. And then you have this. And you finish this. Okay. For the moment, take this here. And you have this one for 0. You have this one for 0. Since this one is plus 20. So we have what? We have the dm by dx equal to plus 20. So it's going to be plus 20 like this. How much the moment here? Moment here minus 0. Minus 0. And it's going to be the area here. That is going to be 20 times the area of 6. So equal to 20 times 6. We have this m equal to 120 kilonewton meter. Okay, that's simple. And then since this one is 0 and the shear is minus 20, so S is minus 20, and then you get this one as your moment diagram. Okay, it's going to be very easy, right? The same thing here. And what important is you got to determine the value of, let me last this. Okay, we got this already. Okay, it's 120, you see, right? I just show you here. And what we have is, since there is the point where the moment of initial change. Okay, this one is project to here, and this one is project to here. Okay. If you draw this for the conjugate beam, let me draw this for conjugate beam. You may put this as the pin and the roller. Since what? Since external roller still the same, external pin still the same. Okay, and on this side, this is 120. What's the value of this to be determined? Since this is 120, okay, and this is going to be 6 Okay, it's going to be similar triangle 120 and times 6 equal to this one. Let's say this is y, and then divided by this. This is going to be 4. So y equal to 120 times 4 divided by 60. If you put this one, this is going to be 15 and this is going to be 80. Okay, the 80 is come. Now, what happened to the 80? There is something happened to the 80 because what? Because at this point we need to separate the elastic weight into two portions. Two portions of what? One is on the left. Okay, one is on the left. Here, that is going to be 80 divided by EI. And another one is going to be on the right. Okay, this one going to be what? This one going to be 80 divided by 1.5 EI. And this one going to be 120 divided by 1.5 EI. And this one also 80 divided by 1.5 EI, but on the other side. Here you have the 80 divided by EI. So your elastic weight gonna be something like this. Okay, with a little bit complicated to compute, but it's not that hard. Since the beam is symmetry, what we have the deflection of the beam going to be large here. Why is large? Because it's only I. Okay, and this one going to be less since it's defect by 1.5. Let me put this one in another color to make it a little bit more understandable. Let's put this with the light blue. So this one gonna have the light blue. Okay, we have very less small deflection because it have a large moment of inertia. Okay, and the other gonna have this. Okay, and then we got to determine what? We got to determine the A sub y part, and we like this. A sub y part gonna be equal to B sub y part because of what? Because the symmetry of the beam. Okay, we just cut it and analyze it. If do this due to the symmetry, we just say that the A sub y palm or B sub y palm going to be the area here. So the area here going to be what? Going to be this one. Okay, and then plus which one? Plus the area here. Okay, and actually you may just put only half of this, so they divide it by a half, but actually you don't need to do so. Okay, let me do this. Okay, this is going to be what? This is going to be our first area, and this is going to be the red one. Okay, that is going to be 1/2 of 4 and times 80 divided by EI. That's the first one. Next, what we have is this one. Okay, and this one going to be have the height of 53.33 divided EI. So it's going to be plus 53.33 divided by EI, and this has the 2 meter. So we're going to times this one by 2. Okay, times this one by 2, and then the last one that you may have is this one. Oh, let's put this one in. Let's put this one in the green. We have this one for the green. So okay, this one for the green. So the height of this is 80 divided by this one. So is going to be plus 1/2 of 2 meter. Okay, and then it's gonna time 80 minus 53.33 divided by EI. Okay, you will get this. I think the first term is going to be calculated easily. Just cut this one, and this one going to be 2. That is going to be 160. Okay, this one, when you times it, it's going to be 53.33 times 2. It's going to be 106.66, and then you get, oh, it's not very good for to have this one to get that, and the last one going to get that. Okay, you get the same thing, and then we have this for the slope at the A. Let me take this one out. Okay, and then we have the result of this. So this is going to be the slope. Oops, theta A equal to 299.33 divided by EI, and also here is theta sub B equal to the same thing. And then you need to determine the Vmax. Vmax going to occur what? Vmax going to occur at the center of the beam. Okay, this is going to have theta equal to 0. And then to determine this, you got to cut the beam by 1/2. And then you may do what? You may take the moment about here. By doing this, we have this one 299.33. So what we have is take the moment about summation of the moment equal to 0, m palm equal to 0. What we have is m sub c palm. Okay, that is going to rotate counterclockwise as a positive. And then what you have is this one gonna go in the same way, plus 299.33 divided by EI, and the distance from here to here is going to be 6 meters, so times 6. And then you also have this one, okay, in the opposite direction. So we have this for 160 divided by EI, as you may know, and 160 gonna have the location here. So this is gonna be what? This is gonna be 4/3 and plus 2. So it's gonna be 4/3 and plus 2. And then we also have for this area, we put this one already, 106.66. Okay, this is going to be in the same direction here. It's going to be plus 106.67 divided by EI. Since it's at here, so the distance here going to be 1 meter. And the last one is this, okay, 26.67 divided by EI. And then the distance here is going to be what? 2 meters divided by 3. So 2 meters divided by 3. You got to be very careful when you put all the number into this. Okay, and then, oh, what we have is what? That is 1, 2, 3. Okay, it's correct. And then we got this for 1102.2 divided by EI. And then you guys can have negative side, right? That is downward, like I mentioned. And then you put this into the equation, and we got this beam gonna defect for 30.8 millimeter. That's quite a lot. No, that's not quite a lot. That is going to be okay. And what I like you to do is you may going back to do the calculation with this beam without the 1.5 I. Just put the same constant I. Okay, you will get the answer on that. Okay, that is going to be the end of the conjugate beam, and we will have more example by writing or by demonstration to you how to solve the problem manually. Okay, that's it.